let's see how far we can go. Oh, and let's start recording. Oh, it is recording. I'm recording. Oh, good, good. Okay, so, and that is recording too. Sorry, extremely warm for some unknown reason. So any questions or concerns before we begin? Our job, any? No? Our job is today is to start from reviewing pointers, going to, reviewing statics one more time. Going through pointers, kind of remind you of what pointers were, and then continue with the rest of the stuff as we are going through the topics. So first thing first, quick reminders of what statics were. What when we say static, what did we mean? When we said static variable, essentially we said that the static variable is a static thing. Anything that is static will get created once, initialized once, and it stays alive until the program is over. But the visibility of a static variable is local to its scope, whatever its scope is. So whatever the scope of a static variable is, that's what it's done. And we show we created a function called va, and we kept calling the function over and over. We would see that it keeps its value and adds one to it as it goes through. That was statics. Did we talk about static methods in the class? OK, so that's a quick review on that. So what is the difference between a static member variable and a static variable? Unlike regular variables, static member variables are shared between instances of the class. So if you create 5 objects out of the class, the static variables are shared between them. So one static variable for all instances of the class. And the perfect example for it was to actually count how many instances are created by adding 1 to the static variable in the constructors and reducing by 1 in a destructor, so you can keep track of the values. The problem comes that people are looking with question marks. Did we talk about this? Yeah. We did, right? And I drew 1 to many, many to 1. Yeah. So, and we know because we have one shared variable shared attribute between all the classes, none of them can initialize it. Therefore, we have to have an initialization done outside of the class as if we are creating the variable, but inside the class. So this MCNT, if it's supposed to be static over there, it should get instantiated as a member of container and being initialized. That initializes it. And we said we can create static methods to access the static variables. But we have to remember that static methods are only allowed to access static stuff and nothing else because of one-to-many thing. If you have one method, it doesn't know which regular method to go to. One static method, it doesn't know which version to go to. Therefore, you can only access static variables, non-static members from non-static other non-static members, not from static ones. Now, we want to talk about pointers, refresh a review of pointers, because we're going to go through different types of pointer things and pointer to pointers and things like that. And I want to first clear in your mind what pointers are. Okay? How many of you have seen my IPC 144 or OOP345 pointer presentation? Okay, so we'll go through it again. So for you guys, it's going to be a review. For others, it's going to be something new. So our objective is right now to let me just bring it over here first so you have it. So first of all, the notation that the presentation is for IPC 144. That's why when you see I create a structure to actually create an instance of it, I say struct something. So ignore that. Okay? You know better. So our objective over here is to start from scratch and design our own pointers. To do that, we need to understand what a memory is. The memory in which you have all the stuff loaded into, the random access memory, RAM, that you have on your computers when things run on, it's an array of bytes. Which in C, we say an array of characters, right? And it has an index. So index 0 is the first byte, first character in your memory, and it goes up to whatever the RAM of your computer is. And even more than that through virtualization. When I say virtualization, I don't mean virtual functions. Some operating systems, when you don't have enough RAM, what they do, they create a file and copy everything from your RAM to the file and then swap. So they use your hard drive as RAM. Then that's when your computer suddenly goes extremely slow. You don't have those. We don't have those scenarios these days because my cell phone has more memory than, like 200 times more memory than my computer when I was actually at university. So you're not going to ever see that, okay? Unless you put some kind of an allocation in a loop and you're not aware of it and you just are dumping into memory, and then you will notice it. But anyways, so when you create a variable inside an application, essentially a piece of memory is dedicated for that, and it's labeled with the name of the variable you have. And when you have a different type of variable, depending on what is the size of the variable, operating system or your program, whatever you call it, puts it somewhere else, and it's going to occupy other places that you have. Having said that, my lady over here is going to tell us what is the address of the var.
It's at 132.
132. So where the variable begins, pass it to. Where the variable begins, that's the address of the variable. How far it goes, it depends on the size of the variable. So if var over here has 4 bytes, dvar has 8 bytes. So what is the address of var over here?
108.
So if I want to put another integer after var, what its address going to be? If I want to put an integer adjacent to this one, what the address is going to be?
It's 112.
112. Well, you're doubting. Go ahead. Loud. 112 with pride. Okay, there you go. Okay, so it's going to be 112. That's obviously what it is. So if I want to put another variable after dvar, it's going to be 140, right? Because it's 8 bytes. Are we all clear on this? All right. And when you put values, that's why when you put values, it overwrites the whole bytes that you have in there. So when I put something in an integer, it overwrites the whole 4 bytes. And in here, it overrides the whole 8 bytes. Are we OK with this? All right. So let's design something to hold the addresses of these things. So we're going to design a new type to hold the address of these things. You do that all the time in an envelope, right? You write an address of someone on an envelope. So the envelope size is always the same. It doesn't matter if it goes to a government building or a small little house. The size of address is always the same. So we don't need to create 5 different types. One type will take care of it. So I'll create something, I'll call it pointer. Let's say the type is pointer. I say pointer PTR. So PTR's job is essentially to hold an address. So when I put 102 in it, it essentially points at address 102, right? but I don't have anything on 102. So if I actually go to that target, that's where you say segmentation fault, memory dump, or you got to have illegal operation happening on your Visual Studio, call the police. So things like that happens, right? So we need to put a valid address over there. Because of that fact, and because of the fact that the name of the variable never tells you where the address is, I need to have another type of operator to extract the address of. So we call that address of var. So PTR is equal to address of var essentially means, if you come, you can see that over there. You're good? OK. Thank you. All right. So address of, we design it to extract the address of a variable. And therefore, and then now that I have the address of variable over here, if I want to access that var remotely using PTR, I cannot just say PTR is equal to something. If I say PTR is equal to something, PTR will change. I need to set the target of PTR, right? So let's call it target of. So I'm going to say target of PTR is equal to 2345. And because I am saying target of, this operator says don't go to the PTR, go where PTR is pointing to. Therefore, var will be set to 2345. Are we OK with this? Down to this point, the design is nice. And therefore, if I print, sorry, it's printf, IPC. If I print variable, it's going to print the value. If I print target of pointer, it prints the same thing. And if I just print the pointer itself, it prints where var is sitting in memory. Are we all clear on this? Those people who are watching it twice, don't do this. Those people who have seen it for the first time, are we OK with this? All right. Are we OK with this? All right. So what if I want to make the pointer point to the double now? So I have to say PTR is the address of dvar. And then I say target of PTR is equal to something, and I want to write the whole thing over there. How can I? Over there, we assumed that it's pointing to an integer, so I put 4 bytes over. How do I know this is? What if it's a float? What if it's a long double? I don't know. From PTR, there is no way for me to know what's sitting at the target. So this cannot work. So I have to fix my design. I cannot just say pointer PTR. I have to say integer pointer PTR. So we know it is pointer, of course. The size is always the same. But I need to tell it that what's something sitting at the end is actually an integer. So all the good things that I have done happens. Now, if I want to create a pointer to hold the double, I can actually create a double pointer PTR, which is exactly the same size. However, the target is different now. Now, when I say dptr is equal to address of dvar, now it's OK. Now I can put some value in it. Because it knows the target is double, it can actually put the value in there. We good? And then everything else happens properly. Are we OK with this? So therefore, give me a second. Having that design, I should be able to say something like integer num is equal to 100, right? Then I should be able to say something like integer pointer is equal to integer pointer, say PTR is equal to address of num, correct? And then I should be able to say target of PTR is equal to 400. So in here, I can say cout num. That's going to print that one. And I can say cout num again. That's going to print 400, right? Correct? Are we OK with this? Not only that, I can address that like that, like to emphasize. I can literally say cout target of PTR, and it's going to print the same thing because it's target of PTR, and therefore it's 400. Are we okay with this? So how did that happen? How did it work, and why we have never used this before? It's easier that because you know pointer is pointer, target of, target of. It's because I put it in here. So I said, anywhere you see target of, put an asterisk. Anywhere you see address of, put an ampersand. Anywhere you see pointer, put an asterisk. So how do we identify what is what? You know what define is. Remember that? Search and replace. So I'm literally saying search and replace. OK? Kind of play the trick. So pointer in C is represented as asterisk. OK? What happened? It's going backwards? Oh, okay. Wait. You're right. I forgot what I did. So yeah, it's presented by asterisk. Therefore, we change the pointers with asterisk, and asterisk belongs to the type. So remember, when you see asterisk after a type, always say integer pointer. Never say integer asterisk. That's what causes trouble. OK? When you want to do ampersand, it means address of. Don't say ampersand. Say address of when it's needed. So you have to say dptr is equal to address of dvar. And that shows exactly you mean address of. And when the asterisk comes again with as a target of thing, then you say target of dptr and target of that. OK? So target of and pointer are both represented by asterisk. I always mention this. How do we identify what is what? So we can say the right thing, therefore our brain can listen from what we say to ourselves before it remembers. It's kind of a feedback loop. Okay? When you look at asterisk and you're happy and life is beautiful, that means you're dealing with multiplication. A is equal to B plus C. Right? Right? When you see the asterisk, it's coming after a type, employee, student, integer, double, it actually belongs to the type. Together, they mean that type pointer. Don't call it an asterisk. It's integer pointer. So what we do, if it comes after a type, integer pointer PTR, double pointer DPTR, employee pointer EPTR. These are all unsigned integers with size 4. That one of them is pointing to an integer, the other one is pointing to a double, the other one is pointing to an employee. So what's the difference? The difference is that if I add 1 to PTR, 4 will be added to it. If I add 1 to DPTR, 8 will be added to it. Right? If I add 1 to employee, whatever the size of employees will be added to it. We talked about it. Alignments and size of and all this stuff. Remember that? If it comes after a variable, before a variable as a unary operator, like -5, -p, whatever, then it means target of. A is target of P. Target of T is X. A is equal to B multiplied by target of C. And E is equal to target of M multiplied by C multiplied by C. Never say E is equal to asterisk M asterisk C asterisk. You won't understand what you're saying. Seriously. Say what it means, and you'll remember it. And I guarantee that you're not going to have a problem with pointers. That was what we had in IPC. OK? So I want you to remember that, and it's extremely important. Remember this fact, that pointers are nothing but variables, like an integer, like a double. They are unsigned variables, and the only difference they have with unsigned variable is the arithmetic, which is essentially adding 1 to a pointer means adding the size of the target. Multiplying it by 4, it means multiplying it by the size of the target. So don't even go there. OK? All these things are done behind the scenes. So just remember multiplication and you'll be fine. Just remember adding up and reducing it, and you'll be fine. So that's that. That was pointers. Pointers and arrays. Like, how does that work? With pointers and arrays, we have the same scenario we remember what the variables are and everything, how it works out. So essentially, I have a pointer pointing to a single variable, right? And then you set it or whatever you have, okay? When you create an array, a contiguous back-to-back series of integers to the number you request that will be created in memory. And it's going to be labeled as something. So that's what we've been taught, which AR0 is the first one, AR1, and they say 0 is the first one because computer programming starts from 0. But that's not really the case. Of course, when I set an index, it's going to set the value of an index. But in reality, when you actually create integer AR5, 6 things are created, not 5. 5 integers and a pointer called AR that is constant that points to the beginning of the array. That's what's created. And that's why when you create an array, you can say target of AR is 2, 3, 4, 5, and it sets this first argument, because you said target of AR, and that's the first variable. And when you say index 2, you are essentially saying add 2 to the address. And when it adds to the address, because it's an integer pointer, 2 is 8, therefore it jumps 2, and that's why. And that's why 2 means third. That's why 0 means first, because adding 0 to the address, that's the first one. That's why indexes start from 0 in C. And that's how it's implemented. And we need to deal with it accordingly. And that's why you can actually use this notation. You can say target of AR plus 2 is 555, which essentially means add 2 to the address, and target of, it's identical to the other one. They are exactly the same. Are we OK? All right. And by the way, because we are on Big Blue Button, if the screen is not good for you, log into Big Blue Button, and you can see it on your screens in front of you if you want to, if it's too far for you or something. Because we are we on Big Blue Button? We are on Big Blue Button, but I'm not sharing the screen, so I don't know what I'm recording over there. So now I shared it. So down to this point, people were just listening to me telling things. I have to put the YouTube one up. Make sure. Today I'm screwing up in recording. In 244, my microphone was off. So, and the other one was on. So probably they're just hearing somebody shouting from afar. Okay. So yeah. Now it's sharing. I don't know. I'm off my game today. All right. So now, oh, somebody ding dong. Some from home? Just joined. Yeah, okay. This is a lab. You're supposed to be here. Oh, you're here? Oh, it's you. It's you guys. I'm telling you, my brain, I hit my head somewhere. You see it's a little injury over there? And I think that's the reason. Okay. Seriously? Okay. Put it together, man. Okay, so let's continue. Save, save, save. Okay, save. Okay, so that's that. So that's arrays. Now, regarding static methods, we said that static methods are they belong to the class. They don't belong to. And with static methods, we say static methods belong to the class and not to the object. Therefore, when you have a class and you want to have some utility methods that deals with the general aspect of all the objects, but it doesn't belong to any individual ones, you use static methods for it. And the CSTR that we created was that. So we essentially I created essentially a class called CSTR. Its job is to replace string header file. So what I'm doing, I'm creating a class called CSTR, and I'm deleting its constructor, which means you cannot even instantiate it. You can just say CSTR scope resolution copy instead of string copy. CSTR scope resolution len instead of string len, and so on and so forth. Allo copy allocates. Read, you can read. you can add str cop. What do we have? We have len, we have copy. You can have, I don't know, str, anything that you have in your string header file, you can add it to this one as a static method, and then use it as your utility. It's a perfect thing. It's perfectly encapsulated. You're not going to override anything, and you can just use it with a scope resolution of this CSTR. And I have it over here because places I have used. And this is something that I wrote that reads from the console in a dynamic way. So you can actually read a C string from the console without a limit. It reallocates the memory. Go through it. It's good for your health. All right. That's that. So essentially, so this is fake pointers. And this is about the array. So when I have an array, I can literally use the pointer notation to deal with an array. And if I point to an array with another pointer, essentially I'm going to have an array with two names. So P0 is AR0. If I add to the value of P by 2, this is going to be in your quiz. So what happens over here? If I add to the value of P instead of the beginning, it's going to actually point to 30. So P0 becomes 30, as if this array only starts from here, right? And if I say P minus 1, it means 20. And if I say P index minus 2, it means go back. From what I said, that essentially index is what is added to the address. If you put negative value, that's what's added to it. Therefore, P will be reduced by 8 instead of added by 8, because each one, yada, yada. And if I run the program over here, you will see. How did that happen? Cool. I did something, it went on the other one, but I don't know how. Anyways. So, yeah. So as you see, when I do P plus 2, so P is actually, so first one is actually showing 40. P plus 2, P0 becomes 30. Then if I say target of P minus 1, that becomes 20. If I say P minus 2, that becomes 10. A beautiful walkthrough for a quiz. Are we good? All right. As we mentioned before, what was that noise? As if something's rotating. Okay. So another example for a static value, the static method, and also talking about references of pointers, something that confused people in OOP345 for some reason. Okay? So first of all, copy over here is a method that is supposed to allocate and copy values in my name that is dynamic. Because allocation and copying has nothing to do with the name, but it's a necessary action to take for dynamic memory allocation, I need it in here. It's my utility. It doesn't belong to name, but it belongs to all names, therefore static. Now that it's static, it doesn't have access to regular values. Therefore, if I want to access regular values, I have to pass them to it. Now, allo copy is supposed to make data point to something. Because it's supposed to make data point to something, it's supposed to change the M data itself. Therefore, I cannot just pass the pointer data, because that's passed by value. I need to pass its reference if you clear your mind of pointers as regular variables, then it's obvious. If you want to change integer data, you pass integer reference. When you want to change into character pointer data, you pass character pointer reference. Therefore, data becomes a new name for whatever is passed to it, and it can change it. And that's why we can, in the constructor, say allocopy mdata and name. The way this function is called is essentially saying allocopy character pointer reference data will be initialized to mdata, and constant character pointer source will be set to name. This is how a function is called. We talked about this in OOP345. When you call a function, essentially the arguments of the function are initialized by the things you pass to them. Therefore, character pointer reference data will be initialized by mdata with definition of reference. Data becomes a new name for mdata. Therefore, you can't change it. Constant character pointer source will receive the address by value. So source and name are two different variables pointing to the same location. I don't need to change the name. I just want to read it, so the address is enough for me. I just need to know where the name is. Therefore, this suffices. I don't need to pass it. So source will get copied into data. Data is mdata. Life is beautiful. And that, ladies and gentlemen, is essentially a review of pointer references and static methods. Are we good? Yeah. Are we okay back there? Questions? Pointer references? Okay. We said that character pointer is a type. It's a reference to any type. If I had over here car data, then I can create car reference data, right? Same thing. Say character pointer mdata, I can create a reference to that. Therefore, if I want to make this attribute point to somewhere different, I can change the reference over here. And because reference is a reference to mdata, it's going to change the same thing. Back to the function implementation. If I actually look at the function implementation, when the function is being called, whatever is passed to the function will initialize the first argument. Therefore, type reference data becomes equal to mdata. Data becomes a new name for mdata. Anything you do to data, mdata will get modified too, because it's a reference to it. And that explains it. Okay? When you want to change the value, when you want to change the target, you use reference. When you just need to know where it's pointing, you get a value. As simple as that. Not at all. SCRCP, oh, no. No, SCRCPY, you don't change the data, you change the target. See, for STRCPY, it's using C string. God damn. I could use the other one. But anyways, C string receives two regular pointers. The only difference is that the second one is constant, the first one is not. So source is pointing to a location, data is pointing to another. It wants to change the target, not the data. It doesn't care what the data is. Here is different. I want to allocate memory and put stuff in it. This one already has memory. I don't need to change it. I just need to change the target of it. Got it? So this doesn't need reference. That needs. Okay? Again, you are giving pointers extra credit. So data is pointing to somewhere, source is pointing to somewhere. Each one has its own value. All you need to do is to copy stuff from source to destination. Right? Therefore, data is not changed. The target is changed. Are we good with that? Okay. What's the difference with the other one? The difference with the other one is that this one is pointing to somewhere. I don't know where. So what happens in allo copy, this is what you do. In allo copy, you allocate a piece of memory, and you have your source that is being pointed to. And you copy everything from the source to this allocated copy, allocated memory. Right? Now you want to change. Now you want to change the data itself. So the place that is pointing to, it points to no more. Now it points here. That's the difference. Here, M data is changed, not the target. The target is a completely different thing. Are we okay? Okay. So next is, what if let's say it's a completely change of venue now. Okay, we are not talking about this. Let's talk about this. Say I want to blindly copy a piece of memory from one place to another. Okay? I have a piece of memory somewhere. I want to blindly copy it somewhere else. What do? All I need to do is to break it down into smallest pieces possible. Who's the talking stick? Oh, you already answered? Okay. What is the smallest addressable unit of memory? Smallest addressable unit of memory. Loud. A character. Fantastic. A character in C. Pass it to the lady behind you. A character in C or a byte in computer science. Are we okay? Now, what is the smallest unit of memory?
A bit.
A bit. Thank you very much. Pass it to the lady. A bit. A bit is the smallest unit of memory, but it's not addressable. You cannot say bit number 32. We'll find out at the end of the semester we're going to change them. How we're going to change them? No, now. But it's not addressable. You have to jump through hoops to be able to change a bit specifically. Of course, when you set a variable to something, you are changing its bit pattern, but you have no control over it. It happens for you. If you manually want to flag a bit to on and off, that's a different ball game. We're going to talk about it later. So to copy a piece of memory from one place to another, the easiest way is to break it down into characters and blindly copy it like this. So I can write a function. I can say copy mem from this location to that location. I'm going to put characters over there because anything can be broken down into characters, right? Anything. And if I want to, for example, copy a piece of double from one place to another, it's going to be a little hard to call it because I have to write casting like crazy, right? I have to say copy mem, reinterpret cast to character pointer the address of B, which is the destination, and it's a double. And I'm going to say reinterpret cast to constant character pointer the address of the source, which is a double. And the size is size of a double. So this is going to be initialized to the address of the destination as a character array. This is going to be set to the address of the source as a character array. And this is going to be its size. One by one, I copy all the bytes. And the result will be, in a painful way, I'm setting B to A. And the outcome is exactly the same. Are we OK with this? How to remove this pain? You can endure the pain in here and let the user just use the address. How? I can pass pure address, an address without a type. When you don't have a type, what do you call that type? Void, right? But when you say void, you mean nothing. When you say void pointer, it means it's just an address, no type. So instead of writing this, you can actually do this. Void pointer destination, constant void pointer source and size. Then create your own array pointers of characters. Do the casting in there. So the user can easily pass the address with no casting. That's how void pointers are used. When you have many different types coming in and you don't know what they are. And by the way, it has nothing to do with C++. Of course, the castings are. Those templated castings, those castings are for type safety that we have in C++. In C, you simply say character pointer destination and constant character pointer, so you just cast it. But in here, you have to cast it this way, so you know what's going on. Are we OK with this? All right. So that's that. So that's void pointers. Representing, what happened? Somebody said professor? Was you? Was it you? Is it OK? Question? OK. You talk like this. OK, so this is an assignment operator. Which side is this, right or left? This is an rvalue. What is this one? lvalue. Got it? Good, let's go home. So that's it. So rvalue, why do they call that? Because that's the general way of saying it. Of course, I can have something like this too. So an A is sitting at right side, but it doesn't mean it's an rvalue. An rvalue is something that cannot be at lvalue, but the other ones you can. You can put an lvalue at right. There's no problem with it, as you see that. But a real rvalue is something that either you cannot or should not be at left. You can't do that. This is a pure rvalue. You can't do it. It's supposed to be at right-hand side. We have another type of rvalue that you're not supposed to put it at left. Say, I have, C string. Why it's giving me an error? Oh, because I didn't include C string. Yeah. So now I have this name thingy, right? Okay. So this cannot be done because 10 is our value. It's literally a syntax error, right? Now I can do something. So actually, let's put it in two different source codes so we don't have too many things at the same place. Give me a second. Give me a second. So now let's have this one over here. So I have this name thingy. It has a constructor, an assignment operator, print, or whatever, right? So we can actually do something like this. I can say name f is Fred, and I can have G and H over here. So I have few things, right? Now, I can say something like f is set to name John. I can do that, right? Now, what is this at right side? It's an object that is about to die. It's a temporary object. That's another R value. Of course, because it's object-oriented, I can do this. There's no problem with it. Why? It is an R value. And you put it in at left. So it's being set to F, and it's going to die. Why? You're not supposed to. So in previous version, compiler actually didn't let you do it because it was a literal value. That's literally R value. This R value is that in future we're going to go up. We're going to actually break it down. That is, if this R value, you can put it at left, but you're not supposed to. Logically, it's incorrect. We okay with this? Now, all these things are detectable. So, and also, when you write something like this, what happens at line 36? Walk through. What happens at line 36? Wait. See, and just to let you know, I do not have an operator created for it. I didn't overload an operator that receives a constant character string it right. Why don't I get an error? Who has the microphone? What do you think, my dear?
It's a hard question. So I think maybe on line 32, we already create an object of it, and then we assign the object with a new string value.
Yeah, that's what I'm doing. So how come it's not giving an error? At left side, I have a name. At right side, I have a constant character pointer.
Yeah.
How come it's not giving me an error? Let me ask you another question. You answer that, you're going to answer this. Or not even that. Can I do this? Can I do line 39? Why? It's a double. This is an integer. What happens?
A cast.
So what does it mean, casting?
Casting double integer value to double.
Casting casts the integer to a double. What does it mean?
Change the type.
No. Yeah, you change it up how? Like 10 becomes 10.5? No, 10 is an integer. What does it do? Let's make it easier. Not easier. I mean, like more. Let's have it like this. What's happening now? So what happens to I? I is an integer, B is a double. It works perfectly. I'm going to have 10.0 in here. How? Take the microphone.
It passes the value of I to B.
No, it doesn't pass anything. It's an integer. It's a double. They're a mismatch. It cannot pass it. In computer science, when you have an assignment, left and right must be the same. You cannot do anything until they are the same. Milady over there says it's going to get casted to a double first.
Yeah.
And I'm asking, what is the meaning of casting? What does it do?
So,
Yeah, how?
but
To a higher, which means temporarily it will change this to a pointer, to a double, does the assignment, and then the double is gone.
Yeah.
Now, give the microphone back to the lady. Now explain this to me again. Exactly as I did this one. What does it do?
Cast the string
Casts the constant character pointer
pointer
to a name,
to a name, to a
does the
temporary-
assignment. How does it cast? It creates a temporary nameless object. Got it? Casting, that's why casting in C is written like this in C++. Not the other way. You don't put parentheses around double. You put it around the type. You are saying create a temporary double out of the integer and pass it. So in this case, what happens behind the scene is exactly like line 36. You see at line 36, John becomes a temporary name. This is exactly the same. Got it? So it creates an R value. Now we can pass it to the gentleman over there. Thank you, thank you. So R value and L value, now we know. So R value is essentially any object that is either literal the temporary thing that is about to die, or a literal value. That's what an R value. An L value is anything that you can set it to something. We're going to break it down. An R value and L value, we have different types. We're going to come to it soon. But down to this point, let's just have it like this. And the good thing over here is that C++ can detect that. The good thing is that the R value and L value can be detected. What do I mean by that? What do I mean is this. So this is that. I just want to make sure that I do. Yeah. So take a look. Now take a look at this, please. Take a look at this. Take a look at this. Introducing a new thing. This is called an R value reference. So actually, C++ can identify what's coming in if it's an R value or not. So in here, I can actually say, come on, A, and I can say, and I run it, you'll see that nothing happens. Why? What happened? Oh, shoot. I changed the wrong file. OK, copy. I renamed it, and I didn't change. Give me 2 seconds. One more time. If I run it, 3 years later, 4 years later, 5 years later, you're going to see that it's going to say 10 is L value and 100 is R value. So the one that is L value will go with the regular reference. The one that is R value goes over there. You can do the exact same thing with an object. Okay? And I have names. Now I'm printing names. Now in here I can have so I can say not switch, which value. In here I'm going to put F, and I'm going to say which value and let's try something else afterwards. Okay, so now if I run it, you'll see that it's going to pick up the right thing for the name too. So Fred is the L value and John is the right value. So it knows that this is a temporary object. It's about to die. That goes to the R value reference. Are we okay with this? All right. Now, I can do this. To force an L value to be an R value. I'm saying move F. And now the second one is an R value. You'll see why. And we can do ref to force something to be a reference if we can. Okay? Now, and also, I want to do this and see what happens. Take a look. I want to see if it works. I said which value Jake. So I have which value? I have 4 of them. That's a constant character pointer. Cannot be casted. Cannot be casted. It can cast it, but the outcome is not going to be an L value. But this one is possible because if it casts this to a name, then the outcome matches this one. So the compiler hopefully does that. And the R value Jake is going to get printed. That shows how compiler tries to cast so hard. Obviously, if I do a reinterpret cast to an integer, because it's a pointer, it's going to cast it and show you the address. But I don't want that. I want this. Are we good? Are we okay? That brings us to rule of 5, not rule of 3 anymore. Okay, we're going to use this to make our code efficient so things happen much quicker. And that happens after these messages, which means let's go for a break. Okay, let's go for a break. So the next day you are coming in, we're going to have lots of lectures to go through, so be aware of it. Where's the big blue button? Resume recording, yes. All right. So now that we have these things, now, please listen to me for a second. Attention, attention, Achtung. Okay. You want a cup of coffee? I have a cup of coffee. Okay? There are 2 ways to give you this coffee. Number 1, I can come to you, okay? You can present your cup, and I can empty my cup to you, and you go. My cup is empty, I throw it away. You have coffee, right? Right? Number 2, I come with a cup of coffee. I'll tell you how the coffee cup is made, so you can make one. Then I tell you how did I make the coffee. Took the beans, grind it, you learn it. You do it. You build your own coffee exactly like mine, and you go. And then I see I have no use for it, I throw my coffee away. That's the second part. The second part is what you are doing in OOP345. Any time you're calling a copy constructor, that's what's happening. Right? The second one, the first one is the one we're going to do now. When you want to get something from another object and that object doesn't need it anymore, you don't need to rebuild everything from scratch. You could just take over their property so they don't have anything. If I want to give you a cup of coffee, I'll give you my cup of coffee. You're gone. I don't have anything anymore. No copying happened. And the passing of coffee, your need to have a coffee is done like that. That's called moving. Instead of copying, we move. How do we recognize when we move? When the object that is coming to us is an rvalue. If the object that is coming to us is a temporary one, I don't need to copy it. I'm just going to take the ownership and empty its property. It's going to die anyway. Or if it's flagged to be moved. So let's do it. We have the rule of 3 in here. I have a name. Just a quick review. My name has data in it. It has a constructor that creates, allocates, and copies information in it. Now I have an assignment operator. Oh, I don't have a copy constructor. What the heck is a copy constructor? Do I have a copy constructor? No, I don't have a copy constructor. It's rule of nothing. Let me yeah, there you go. That's better. Okay. So that's the code. Now I have a copy constructor where it actually checks to see if the other thing has anything. If it has it, it will do an allocate and copy. So it copies. And you remember what allocate and copy was. It receives the reference of this one, allocates and copies. So it does that. So copy constructor, the assignment operator does an allo copy. The reason is that my allo copy actually deletes the destination beforehand. So you can actually use it for the assignment operator. You see that? So it deletes the destination, so I'm good. So I use this so that I can use it for assignment operator too. And I print and so and I have a virtual destructor over here, so life is beautiful. I do have rule of 3. What is rule of 5? Rule of 5 says you should be able to do a move copy and a move assignment too. What does it mean? So I will say the signature is exactly like a copy constructor, but the difference is, first of all, what it copies is not constant anymore, because you want to be able to take its ownership and remove its ownership. So first of all, it's not constant. Well, what did I do? What did I? Okay. Secondly, it's an rvalue reference, not an lvalue reference. Therefore, it detects what's coming in is about to go away. What do? I'm going to check. Does the other one have anything? I check. Does the other one have anything? Because I already initialized it over here to 0. So does it have anything? Yes, it does. If it does have anything, I'm going to say my value will be pointing to their value. Right? So I'm just pointing to their data. And I'm going to say, you are pointing to that one no more. Done. No copying is happening. I'm saying, you have a value, mine now, and yours gone. I take the ownership. Same thing with the assignment operator. So with the assignment operator, if I want to have a move assignment, so move constructor, move assignment is much more simple than using, doing, what should we call it? The regular stuff, okay? So in here, I'm saying, first of all, I want to move the other one. and it's a reference. Am I the same thing as the other one? No, I'm not. So first, I'm going to wipe out mine because I don't want mine anymore. So I'm going to delete my value. Right? Now that my value is deleted, what do? I'm going to go mValue is set to n.mValue. Okay? I can check to see if the other one is null or not too, if you want to do that. Sure. Okay? But I'm just. Okay? And after this, I'm going to say mValue is null PTR. I take the ownership. I don't copy anymore. So the mistakes you made in OOP345 and caused problem, over here actually is what you're supposed to do. So you're saying, delete mine, let me point to the data of the other one, and make the data of the other one null. And we're done. Now, if you do this, what's going to happen? If I say name, F is Fred. Who has the microphone? OK, what's going to be called in here at line 55? You don't need to look at the source code. Assignment at the moment of creation is?
Assignment at the, sorry, what?
Assignment, you can pass if you're OK?
I'm a little confused.
OK, so at the moment of creation, when you assign that thing that you are creating to a value, what are you doing to it? You are initializing it, right? Initialization is? You know the answer. When I pass, when the other person answers, you'll remember, because your face shows me that you know. Yes?
Copy constructor will be called.
No? Close enough. Give it to the next person. It's not a copy constructor. It's a
Constructor.
constructor that accepts a string. So literally, this is identical to or these three are the same, identical. We good? Are we OK? All right. So I'm doing this. See that? OK, or this one. Now,
Copy.
that's copy constructor, right? But is it a move constructor or a copy? What do you think?
Copy.
It's copy, because f has its own value. We don't want to lose that value, right? So now if I actually do over here like this, come on. If I do this, you will see that after all this good stuff that I have done, they're both Fred, right? Now take a look at this. So you see what my print is doing, right? If m value is not null, it's going to print the m value. If it is null, it's going to print empty. Are we good? Now see what happens. So in here, I'm going to say, now I'm going to run it. See what happened? F's value is gone. F's value is gone. I moved it. That's the difference. This one copied. This one moved. You see that? Are we OK with this? All right. So, and we have to, but this is when you do it manually. But if you do something like this, if you do something like this, G is equal to Jack, what's going to happen now? Take a look. Wait. Actually, I have it already. I'm going to walk through it, though. So this is what's going to happen. Okay? It comes right over here. I have assignment, and I have a constant string. We know that's going to get casted, right? So this is what's going to happen. It comes over here. No, that comes over. It comes over here. Out of value, Jack will be created. So it creates a temporary nameless object called Jack, right? Name out of Jack. And now at right side, I have a temporary nameless, assignment and G. Where it's going to go? To the move assignment. Because it doesn't want to copy the damn thing away. It's going to just die. Who cares if it has something or not? So it comes over here. It deletes its own value. It gets the value of the other one that is Jack, make the value of the other one null, and it comes out. As soon as the assignment is done, that nameless is about to die, right? When it comes to the nameless, value is null. It doesn't need to delete anything anymore. Therefore, lots of time is saved. You follow? If we didn't have this, first an object is going to get created. Then the object is passed to that one. Then the object gets copied. That object is deallocated. The object is created. It's even worse when you return something by value. Oh my God, if you return something by value. Let's see that. So let's stop. We know exactly what happens. What is this? Oh. Let's say I have something like this. Name, make, Jane. I don't know. I'm making Jane. So in here, I'm going to have name is equal, name n is equal to Jane. And I say return n. So let's walk through this. When it comes in here, it's going to create a Jane, right? Now it wants to pass that n out. The n is supposed to come from this and go out, right? If it just passes it out, it's not going to be passed out because n is about to die. So what it has to do, it has to create a temporary nameless object out of n because n is about to die. It gets copied into a nameless, and then n dies. Now I have an n name that got created out of that one, a copy, with all the memory allocation. Then that's going to be passed, for example, over here to G. Now the temporary nameless is here. It's going to get passed, copied again, and passed to the assignment operator or whatever. Or if we had something like, say, if I had something like this over here, and I said, now that's even worse. That temporary nameless will get copied into this, another copy. And then that's going to, with move constructors, because this is all detected that they're moved, instead of copying, one by one they're going to get moved. Therefore, you don't have that all that memory, dynamic memory allocation. Let's walk through and see actually what happens. So I'm here. Whoops, wrong button. There we go. There you go. So I'm right now over here at print name. So it goes over here. Obviously, a constructor is created a name, and now it's returned. As soon as it wants to get returned, it comes to print name, right? You see that? And name is printed. One more time. Sorry about that. So it comes over here. That's created. It goes right over here. And it's printed. And one object is deleted only. So no copying, nothing. Poof, everything is happening through move. Yes?
Do you still need the other ones?
Oh, yes, in case you want to copy. In case you really want to copy. If you pass something by value, just by value. If I do this, it will be copied because there is no request made to move it. And I need the copy afterwards, whatever. Or maybe you want to change it over there and print it somehow. So again, rule of 3 changed to rule of 5. Whenever you have an object, a class with resources outside of its scope, you apply rule of 5. And I'm not going to mention it anymore. This is the last time. I'll give you a class, and I'm going to say, apply, like, this is a class over here. Make sure no memory leak is going to happen. As soon as you hear that, you have to have rule of 5, not rule of 3 anymore. You have to apply everything to it. Okay? And that's that. And by the way, rule of 5, if you want to reuse your code as you did before, in rule of 5, and in here, it's going to tell you that there's a warning in here. Well, you'll see later on. And it says add no exception over there. So in here, it says write this. Okay? For now, any move constructor that you create a no except at the end. It's something that you're supposed to do. What does that mean? Doesn't matter. For now, just if you don't write it, it doesn't matter. Okay? It's just a minor warning at the moment. Later on, we'll understand what exceptions are, and we'll see. So if it tells you what that's the warning, just add it to it. I'm not going to add it now to confuse anybody, but if it tells you, I have 5 minutes. So if you want to reuse your code as we did, so for example, for your copy constructor, you do this. And it's a very usual thing to do. So you go name, const, name, reference, n. And in here, you say operator equal, and you put n, right? That's how you reuse your code. When you are doing rule of 3, correct? When you are doing rule of 5, if you want to reuse your code, make sure you do this. If you don't write that, it doesn't know it has to move it. It calls the other one. Okay? So if you are reusing your code for your move constructor, make sure that your move constructor calls explicitly the move assignment. Because if you don't mention it, it doesn't know you don't want to copy it. It's going to copy it. Okay? That's why we have the move. Are we okay? And that's rule of 5. Are we okay? Questions? This is a little ahead. If you look at the weekly thing, this is not here. It's, I think, for next week. But because you learned the rvalue reference, I think it fits to be taught now, not next. So if you read, you're going to see move assignment and move constructor, I think, for the next one. So the next day you are coming in, we're going to talk about aggregation, unions, alignment, and things like that. Okay, we're going to go through all those things that we didn't talk. So the next time you're coming in, we are going to talk about aggregate initialization, range-based loops, unions, enumerations, pointers to pointers, cloning, and inclusion polymorphism, and all the good stuff. Okay? And more. Okay? So questions? Suggestions? Objections? Pardon me? No, I'm not going to do that. Too many cheatings happening. I don't want that to happen again. I'm sorry. He says, don't. He says, please don't do that. That you cannot go back to a question. Oh yeah. Yeah. So too many. Unless I create 20 different versions for every single one. If I create more than 20, then I'm gonna let you go back. So each question is 20 versions, if I can do that. But 20 versions, really? You know how long I have to think? If I can. Oh. Yeah, I know. Even the best people cheat. Yeah. It's in our blood. As soon as we become student. Have a beautiful day, everyone.